All right, so now you're expert at the three phases and all the transitions between and the energies involved. What if you wanted to summarize that in one big picture? A phase diagram is what that's called, and some of you future engineers are going to need to read those. Now, it's not very difficult. Think of a map, except north and south is pressure, and east and west is temperature, and it's separated into states, which are the states of matter. Let's talk phase diagrams, guys, right now. Well, hey everybody, hey, we're talking phase diagrams today. Welcome back. We're ready to polish off the chapter 10 in the OpenStax text, or the one with intermolecular forces, yada yada. So here's the thing, folks. If you can read a map, you can read a phase diagram. That's basically what it is. It's a map with pressure on the y-axis and temperature on the x-axis. And if you cross a line, you are going through a phase transition or converting from one state into another. It's kind of like a map of something with states on it. Hey, we're in Indiana now. If you cross a line in a phase diagram, there's no welcome sign that says like welcome to liquid or whatever, but you get the idea. I'm going to pause for a second and show you a garden variety phase diagram that's just generic right here from your book. Okay, now what I would like to do instead of using that generic version, I'd like to take something relatable like that. CO2. You know a little bit about CO2, so this is going to be the phase diagram of carbon dioxide. It's in the OpenStax textbook. And so let's take a good old look at this. And first of all, let's find ourselves. And I do got to warn you. Sometimes, folks, you're going to find that not everything fits perfectly on a phase diagram. So you take a look at that y-axis. You notice it's logarithmic? Okay, well, that's how it goes. In order to fit everything on, they're gonna basically squeeze that axis together, whereas this is linear, the temperature is. So why don't we find ourselves? We're here at room conditions. So let's see where carbon dioxide would be in this room as I breathe it out. We would be, let's call room temperature 25 degrees. 100 kilopascals is actually pretty darn close to an atmosphere. I think an atmosphere is 101.3 kilopascals, and of course we're less than an atmosphere. So if we trace that across, we will be at 25. We're right there. And you will notice that we're pretty well in the gas phase of carbon dioxide. A couple little things about phase diagrams. There is another cute little reference point called the triple point. So if you take the intersection of solid, liquid, gas, that is called the triple point. That is going to be a temperature and pressure. I'll do the best I can. We'll call this minus 70 degrees C. And then we'll call that pressure, we'll call that about room pressure, about 100. So 100 kilopascals. What's the big deal about the triple point? It's a way in one set of data to kind of describe the substance. So the lower the values are for the triple point in both pressure and temperature, the greater the intermolecular forces are going to be. So if something had a triple point that was really, really high temperature, You could say, well, that's got really strong intermolecular forces. Now, we know that carbon dioxide's a gas, so it must not be tremendously high in intermolecular forces. So triple point is just a way to sort of describe the substance and you know, where that all fits in. Let's take a trip in mental. This will be a thought experiment, all right? And when we're doing a thought experiment, make sure you're wearing your thought safety glasses. I'm going to go capture a container of CO2. I'm going to put it in a cylinder, and then I'm going to push on it. So I'm not going to change the temperature. I'm just going to do this at room temperature. And I'm going to increase that pressure to a little bit south of 10,000 kilopascals. So what's that going to be? That's going to be 100,000 times, make sure I'm saying that right, 10,000 times, it's going to be a lot more than room pressure. I said 100,000 times, but it wouldn't be if I increased it from, it'd be more like 100 times, I should have said, sorry. So I'm going to increase the pressure 100-fold to like 100 atmospheres. What's going to happen is it's going to liquefy. And maybe anybody out there play paintball? Well, you know, if you take a CO2 cartridge, or if you have like those little bike pumps that pump your tires up in an emergency. CO2 cartridges, if you shake them, that's a liquid in there, folks. And that's because they're pressurized a great deal. I suppose if you were to even go further, you could solidify it. And so you wouldn't even need to cool down dry ice to get it to be dry ice. Why do they call it dry ice? Well, you notice that if we're around here, actually we're pretty close. The triple point's a little bit above, I think, 100 kilopascals. But if you cooled dry ice down a lot, so we're going to go left. So now we're going to take another thought experiment. We're going to cool it down to right there. CO2 doesn't even go at room pressure. It doesn't even go through a liquid. And that's called sublimation. So if you take dry ice, which they use in shipping because it's a lot cleaner than using regular ice, you will find that it just leaves CO2 behind, which is really kind of a groovy thing. If you ever play with dry ice, it's fun stuff. If you go get it at the welding place, you can buy a big block of it, or if you go get an ice cream cake, or you could buy it at some grocery stores. It'll be this solid stuff, and boy, don't put your hands on it for too long. It'll burn you, it's so cold. But it'll go directly through sublimation at room conditions. So that's a little bit of, we can get all this from the phase diagram. So my expectation of you is that you can find all this stuff. What are the phase transitions at any pressure, at any temperature? If you were to push on it, increase the pressure. If you were to heat it up and increase the temperature. This right here, there's a spot where the liquid just can't happen anymore. That's called the critical point. Critical point. So everything has a point where the solid, the gas liquid line just sort of ends. And by the way, if these weren't labeled, you could find them, because hey, what phase would be heavily favored at a big pressure? That would be solid, right? Solids are more dense than liquids normally. We'll talk about an example where that's not the case. And so you could, if these weren't labeled, you should be able to say, hey, gas is where there's very low pressure and very high temperature, and you could find that. But there's a point where if you heat something up, it won't be a liquid anymore. It's called the critical point. And sort of the fourth phase of matter, what that abbreviation is for, is called super higher than critical fluid. Sounds kind of Star Trek-y, doesn't it? Well, not if you drink coffee. There, I'm going to try to get the coffee people on board with me. Unless you drink tea, then it's going to put you in a spot of bother. But coffee can be decaffeinated a whole bunch of different ways. The cheapest way, which I'm not a big fan of, is, even though I'm cheap, is to just take beans and immerse them for hours in a solvent. And the solvent is stuff that ain't good for you, folks, like dichloromethane. I smelled a bunch of that stuff in grad school. It ain't pretty. But the other way that's a little bit more expensive but much greener is to take supercritical CO2. And now a supercritical fluid is hot, and so there's a lot of kinetic energy, but it's also dense. And so supercritical fluids are like a gas that's dense enough to act like a liquid, and it does a lot of good extraction or dissolving of the caffeine, which, by the way, what the object of decaffeination is, you want to take out caffeine and leave everything else behind, and CO2 is pretty selective at dissolving caffeine. So that's a little bit about the CO2 phase diagram. We're going to do two more. Let's take a look at something weird, which would be water. All right, folks, there is water. Weird, wacky water. I'll explain why it's weird and wacky. I just realized that I didn't really perfectly explain the triple point last time. So you see that the triple point of water is somewhere around 0.6 atmospheres. Excuse me, that's pressure in kilopascal. So it's really low in terms of pressure, and pretty low in terms of the temperature as well. But the triple point is also the point where you theoretically would have solid, liquid, and gas all there present harmoniously, I guess I want to say, in equilibrium. Nothing would end up being melting, vaporizing. It'd all be in equilibrium together. You'd have solid, liquid, and gas. This would be kind of like if you went down to Cincinnati and you went to the right place, you could actually dangle an arm in Indiana and then put a leg in Kentucky and then have another arm, let's make it so you don't fall down, in Ohio. You'd be in all three states at the same time. Of course, you'd probably be balancing on a boat too. That would be dangerous. But nonetheless, you could actually be in all three states at one time, and the triple point is where that substance at that pressure and that temperature is in all three states at the same time. Now I'm going to explain to you why water is weird. If you notice the difference between the solid liquid line like that of CO2, it's going forward. This line right here, it's curving forward. Water's goes backwards, and that's weird because I just got done saying that the highest pressure generally favors the densest phase, which is true, but water is weird because the liquid's denser than the solid near the freezing point there. So the best analogy I can use to make this seem important to you is that when you freeze water, its pressure, its density goes down, and here's why. I'm going to show you a diagram of water molecules lining up and making hexagons, because hydrogen bonding makes the hydrogens weakly attach to the oxygens. So that was the structure of ice, and that structure of hexagons takes up more space, and there's wasted space inside the hexagons. And so what happens is, let's say it's wintertime, and you want to go ice skating. When you are ice skating, you are not actually ice skating. You are hydroplaning, because what you're going to do is you're going to take all your body mass and you're going to concentrate it on a certain point. Now let's assume that we're here, we're below zero, it's frozen ice. And what you're going to do is you're going to take all your weight, concentrate it on a blade, and, well, of course we're going to be at higher pressure. Let's start here. Let's start here. Oh, that's what that little, let's start there. All right, we're at a cold surface of ice, and 101 kilopascals is pressure, regular pressure. And now you're going to concentrate your whole weight on the ice, and you are going to melt it. And at the molecular level, your weight concentrated on a very thin blade causes a very large pressure. That pressure collapses all those hexagons and makes the denser phase which is liquid. And then you're going to skate away and it's going to refreeze again. And so when you're ice skating, you're actually liquid skating. But don't point that out at the rink. People are there to have fun. So nonetheless, that's what's going on. You can actually put pressure on ice and it will melt. And so the weird quality of water is that solid liquid line slopes backwards. Hey, let's find out where we are. We're at 25 degrees C and we're solidly in the liquid phase. If we heated it up to 100, we'd be at the boiling point. What if we're on top of a mountain? Boiling point goes down. Sound familiar? What if you're in your Aunt Bee's pressure cooker? Boiling point goes up. See how the boiling point depends on pressure, like we said earlier? So when you cross that line, that would be the boiling point. Critical point of water is pretty darn hot, 374 degrees Celsius. And up here would be, they didn't make it, up. Supercritical fluids always in the upper right corner. And so that's a little bit about water. You will notice that the pressure changes the boiling point a lot more than it changes the melting point. But nonetheless, that's due to the slope of those lines. So get acquainted with phase diagrams, and here's what I'm going to do next. As our last thing, I'm going to pull out of the homework problems carbon. So let's think about carbon. And I'm going to show you the phase diagram of carbon, but I first want to say that there are two forms of carbon solid. You got graphite, which we make pencils out of, and you got diamond. Both of those carbon. You don't think of diamonds being carbon, but they are. So take a look at this phase diagram of carbon right now. Okay, so did you notice that there was 4 phases there? One of them is gas, one of them is liquid, but then there's 2 phases that are solid. So one of them is graphite and the other is diamond. Now, where do we get diamonds from? And how are they made? I'm going to give you a hint. It ain't low pressure. A diamond gets squeezed into its shape of a network solid because the weight of the crust of the earth is pushing on it. And so go find on the phase diagram where you think graphite is, and where you think diamond is, and where you think liquid is, and where you think gas. And then after a little bit more, like now, I'm going to give you the answers. So now, hit pause or whatever. Go mentally figure out which one is solid graphite and which one's diamond. Well, right now, I'm going to give you the answers. Here they are. Are you ready? Don't cheat. Go back and try to do it first. Oh, I can't control you this way on video, but what you did is what you did. Here's the answers. Make sense? Diamond should be where high pressure is. So that corner of the phase diagram. And of course, you can always find gas. That's where high temperature, low pressure is, in the other corner. And then liquid would be kind of, over in that corner, but up higher. And then graphite would be the other one that you just kind of figured out there by process of elimination, which is fine. Hey folks, guess what? Solids are next. So do me a solid and let's go ahead and peek into that next part of solids, and then we're gonna end up really being done with this very lengthy, very, very detailed chapter. So, take care of each other. Be nice. The earth is not flat. Bye.